entropy generation and balance equations for closed and open system. And we'll talk about how do entropy gives the direction. So second law we talked a lot about direction of natural processes. That part it will be more clear in this chapter. Okay, so second law can fully be understood once you are clear with entropy. So we'll try to cover that in this chapter. Okay, now the first law is understood to be the law of conservation of energy. Okay, it says that energy of the universe or any isolated system is constant. So this is the basic crux of the first law. Okay, now what about the second law? Second law is actually the law of increase of entropy. Till now we are talking in terms of heat engine, heat pump and all, but the essence, the crux of the second law is that it says that entropy of the universe is always increasing. Okay, for an isolated system we can say that entropy is constant or it is increasing. So we'll look at them step by step. First we need to define entropy. So the question is, what is entropy? So before we go to that, let us get some background. Let us talk a bit about heat engines, heat pumps, and then we'll gradually define entropy, and then from entropy we'll go to second law. So let us look at the Carnot theorem. That this theorem we studied in second law. Okay. So Carnot says that of all heat engines operating between a given constant temperature, TH and TL basically, none has the higher efficiency than a reversible engine. The corollary was that efficiency of all reversible engines are same when TH and TL are constant. Okay, so in summary, I can say that for a fixed TH and TL, a reversible engine will have the maximum efficiency and all reversible engines will have the same efficiency. This is the summary of Carnot's theorem and its corollary. Okay, everyone is clear with this? This we covered in the second law. Right? Now, let us, we have not proved it that time, let us prove it now. So let us say that we have two heat engines, EA and EB. Okay, and let us say that EA bit any engine and EB is a reversible engine. Okay, so EA could be anything. Let us say EA is irreversible and EB is reversible. Now, we need to prove that reversible efficiency is more than irreversible efficiency, right? Now, let us assume the reverse. Let us assume the opposite. Let us say that efficiency of irreversible. So, A is irreversible or any engine basically. The efficiency of A is more than efficiency of B, where B is the reversible engine, right? What it means? So if we are getting the same, let us say we are getting the same heat supplied to both the engine and heat rejected is different. So if I say that efficiency of A is more than efficiency of B, does it necessarily says that work done by A is more than work done by B?
Yes, sir.
Yes, because they are getting the same heat supplied. Yeah. So because since they are getting the same heat, QH and QH, that's why if the efficiency of A is greater, then work done by A is also greater. Also, the heat lost of A will be greater. Sorry, this will be opposite. Heat lost of A will be lower. Let me make a correction. Okay, because A is doing more work, so it is losing less heat. Fine. Now, let us say that I reverse this engine. Okay, B anyway we know that B is a reversible engine. So let us say that we reverse B and we get a reversible heat pump or refrigerator which is working like this. So let us say the heat supplied to H remains constant and it now needs WB to perform the heat transfer, right? So what we have studied in the second law, similar to that, we can say that for the source TH, okay, it is giving heat QH to the heat engine, to this engine, and it is also receiving heat QH. So I can remove TH completely. I can say that QH is supplied and that QH is supplied to this. Okay, so we can say that we can have an equivalent heat engine which is producing some work. Okay, WA minus WB, because WA is more than WB, right? That is what we have discussed in the last slide. So this is positive. So it is giving some net work. Okay, some positive work is provided by this equivalent heat engine, and the heat exchange is the difference between QL and QLB. Okay, is this fine for everyone? What we are trying to do here?
Yes, sir.
Yes, sir.
Okay, do you see any problem in the second figure?
Sir, only one reservoir.
So it violates second law of thermodynamics,
Yes, sir.
because we need at least two reservoirs. So since only one is there, that means that the assumption is not correct. The assumption that we made originally, we assume that irreversible efficiency is more. That is not correct. So what is correct? Reversible is more than irreversible. This is the correct hypothesis, or this is the correct form of equation. Okay, so what we have done is we have assumed the contrary, and we have ended up in an impossible situation. So this is generally what we do in mathematics. So we say that the hypothesis is wrong, and what is right is this is right. Reversible efficiency is more than irreversible efficiency. Is this clear to everyone?
Yes, sir.
Okay, moving on. So this is what we got in the last slide. Now, if QH is the same, okay, so what will happen is the heat lost by irreversible engine will be more than that of the reversible engine. Is it clear?
Yes, sir.
Yes, sir.
Because heat supplied is same, efficiency of reversible is more, it will perform more work, so the heat lost will be lower, and it performs less work, so it will lose more heat. Okay, now let us take a cyclic integral. Let us say for the complete cycle, I want to calculate what will be dq by t. Okay, this is something which I am interested in. So for the complete cycle, there are only two processes where we exchange heat. One is heat coming from TH, and other process is heat getting lost to TL. So dq is QH for this. QH is coming at temperature TH. QH by TH minus, now this is heat lost. So I'll write minus QL. Minus QL by TL. Is this fine? So if I want a cyclic integral of dq by t, it will be, this is for reversible engine, QH by TH minus QL by TL. Is this fine? For this, for any cycle for on which heat engine is running, this is the equation what we have. Is this clear to everyone?
Yes, sir.
Okay, now this will be 0 for a reversible engine. Why is that so?
Sir, heat is proportional to temperature.
Yes, because we have heat is proportional to temperature. This is how we have defined the Kelvin scale. Now, for a irreversible engine, this will be less than 0. Can anyone explain why?
Sir, because QL
Because
is
QL
less
is greater and
greater than
negative part is bigger, so it is less than 0.
Yes, this part is same. Okay, because the same heat is getting supplied to reversible and irreversible. Now we have said that you lost is more, so this will be more, and TL is same for both. Now if it is QL of reversible, it will be 0. Since it is QL of irreversible, it will be negative. Okay, so for an irreversible engine, I can say that this quantity is less than 0. Okay. Now, in summary, I can say that for any engine, QH by TH, for any engine, QH by TH minus QL by TL is less than or equal to 0. It will be 0 for reversible, less than 0 for irreversible. So I can summarize that for any engine, this holds true, right? Or I can say this is the cyclic integral, right? So instead of writing this, I will write the cyclic integral of dq by t. I can say that this cyclic integral is less than or equal to 0 for any engine. Okay. We can also show that this will be true for any heat engine, heat pump or refrigerator. Okay, this statement holds true for any device we have. And this is called Clausius inequality. Okay, so we have proved for the heat engine, heat pump or refrigerator. I give you as a homework. You can try it and see whether you are getting this or not. Okay. So for any device, any cyclic device, we can say if you integrate over a cycle, dq by t is less than or equal to 0. Is this clear to everyone? Any questions on this? You people are there? Yes.
Yes, sir.
Yes, sir.
So is this clear how we have ended up with this inequality?
Yes, sir.
Yes, sir.
Fine. Now, this is equal to 0 for reversible and this will be less than 0. Then the cycle will be irreversible and possible. Okay. And if suppose some example you get where this is more than 0, that will not be possible and it will violate the second law. Okay. So this is the use of this cyclic integral that you can judge. You can determine whether the process is reversible, irreversible or not possible. You can simply integrate. You can take a cyclic integral of dq by t and you can check what sort of process is that. Okay. Now let us say that I take a cyclic integral of dv. Will it be 0?
Yes, sir.
Okay, because dv is a property. Similarly, dp or any property I take, if I take a cyclic integral, this will be 0. You should go and check back your second chapter. We have discussed when we talked about property. We define property in this way that if you take a cyclic integral, if you return back to your initial position, then the cyclic integral will be 0 for any property. Right? Now we are also getting dq by t is equal to 0, cyclic integral of that. So it might denote some property. It might be referring to some property. What is that property? We'll define entropy to be denoted by that. Okay, so we can say that dq by dt is ds. This is our one definition of entropy. Heat supplied divided by temperature at which it is here supplied. Okay, and we can write for a process going from 1 to 2, I can say that this is equal to ds from 1 to 2, which is S2 minus S1. Now I have written inexact differential, how it can be ds. Can anyone tell me? What happened? You people are not attentive today, or this is not clear? So how ds is not inexact, dq by t is inexact integral. dq is inexact, but ds is not. Why?
Because its surface integral is 0 So it goes through that by same path.
No, it is not surface integral. It is a cyclic integral. So integral taken over a cycle. So for example, we draw it. So suppose we have a cycle. Could be any process. Let us say only two processes are there. So when I'm saying cyclic integral, I'm taking over the full cycle. So I'm returning back to the original position. Let us say I start from here, 1, I go to 2 using this path, and then I come back to 1. Okay, so I take integral over this full path, then I call that cyclic integral. Okay, so cyclic integral for any property is 0. Now, dq is anyway, it is not an exact differential. Dq is inexact because it depends on the path. But when you say dq by t, it becomes a property which is entropy. Now, property is always exact differential. For example, the same thing we did with PdV. Okay, dw d is inexact, but when we do PdV, we say that P is exact, dV is exact. Okay, same way dq is inexact, but dq by t is exact. Is this clear?
Yes, sir.
Okay, so this is basically how we define entropy, delta S. Okay,
Sir, sometimes dq by t is negative also, then how it considered as property?
we will come to that. So dq by t, we'll come to that. So this is basically defined for a reversible process. Okay, first talk about a reversible, then we'll go to irreversible. Okay, just wait for the next slide. So this is actually the question what I wanted to ask and you asked. So what about irreversible? Okay, now tell me if it is a cycle. Okay, I'm trying to calculate for some property. Let us say, let me draw it. So let us say that I have two processes, 1 to 2. Let us say this is path A and the reverse process is path B. Okay, so if I take a cyclic integral of dV for this cycle, what it will be?
0.
Okay, now for irreversible process, let us say instead of B, let us say B is reversible. I have another path. Let us say this is C. C is irreversible. So if I do a cyclic integral over irreversible process, what will happen? What will be my dV?
So then also 0.
Then also 0. Right?
0, sir.
So for any process, the cyclic integral of a property will be 0. And entropy is also a property. Okay, or we can say that for any process, dV will be V2 minus V1. I don't care whether it is reversible, irreversible. That is, I will take the difference. Okay, if I go from 1 to 2, the dV is V2 minus V1. Similarly, for entropy, for any process, whether it is reversible or irreversible, ds will be equal to S2 minus S1. Now, we want to see what is the difference between reversible and irreversible. So for that, we'll go to Clausius inequality. Okay. So this will be different. What will be different? This will be equal to delta S for a reversible, but it will be less than delta S for irreversible. Okay, so I hope this answers your question. So sometimes let us say that dq is negative, but for all the time, if it is an irreversible process, it will be less than entropy. This. Okay. So can you repeat your question or you got your answer?
Sir, I got it.
Okay, fine. So Basically, for reversible process, delta S will be equal to this. For irreversible process, delta S is more than that. Okay, you are losing more entropy than dq by t. And we can say that for any process, delta S, which is this, will be more than or equal to dq by t. Okay, so for reversible it is equal to, for irreversible it is more than that. This is true for any process. So this is an important relation you should remember, that ds is equal greater than or equal to dq by t for any process. Okay, now this brings us to principle of increase in entropy. Okay, so what we have seen is that ds is more than dq by t for any process, whether it is reversible or irreversible or any process is there. Okay, now can I say that ds for isolated system is more than 0? Can I say that or no?
Yes.
Okay,
Yes.
because for isolated system this will be 0.
Hmm.
So ds of isolated system is always greater than or equal to 0. It is actually, it will be 0 if it is if there is no heat transfer is involved for a reversible process, and it will be more than 0 for irreversible process. So what we can summarize is that entropy of an isolated system can never decrease. It could remain constant or it could increase, but it will not decrease. Or we can say that for the universe is an isolated system. Okay, so we can say that entropy of the universe is always increasing. This is the one of the summary of your second law. Okay, so
Sir,
yes,
so I have a doubt in one of the previous slides where you written cyclic integral of dq divided by t is equal to q
this
q1
one.
by t. No, sir, previous.
Okay,
Sir, the
what
starting one.
you are doing till now?
No, sir, it just came to my mind. Sorry, this one, sir, QH by TH minus QL by TL. So how
Yes,
can we assume that QH heat is supplied at a constant temperature TH? Uh,
that
so
is
it,
the assumption. That is how we define.
see,
In the first line, I said that let us say we have pH. Let us say we have QH. Okay,
okay, so, so it's from
this
the
I'm making.
reservoir. It's from
This I'm making
reservoir.
it different.
Yes, sir.
Okay,
Yes, sir.
let us go back to the viewer. Okay, so Rudolf Clausius. Okay, so he was one of the founding figures in thermodynamics. He summarized the first and the second law as, okay, this is written in German. So let us look at the English interpretation. So what he said was that the energy of the world is constant. This is which law? First or second?
First law of thermodynamics.
First law. So the first law, it says that it can be summarized as the energy of the world or universe is constant. The second law can be summarized as the entropy of the world tends towards a maximum. Okay, or in other words, I can say that it increases. It is always either constant or increasing. Entropy can never decrease of an isolated system or of the universe. So this is the basic summary or second law in a nutshell. Okay, with that, let us stop for today. I want to discuss if you have any doubts.